Hello everyone, welcome to Solve classes. This is Tushar Shaw, and in this video we will be continuing to solve the BHU PET 2020 questions that we were solving since the last 14 videos, I guess. Okay, so in the last video we did up till question number 14. So let us I'll not be introducing the BHU paper in this video because I have done it quite a lot of times in the last videos. So let us skip it for this video, because the question that we have, that is question number 14, is a kind of huge one, so we'll be requiring quite a lot of time for that. So in the next video we'll be again then talking about the bit of the paper, and then we'll be starting the video, the question solving. Okay, so let me just show you the question number 14 and 15 that we have over here. That is, which conformation of cyclohexane is the least stable? Okay, which that is chair, half chair, twist boat, boat. Okay, so let me just firstly explain to you what are the all the types of conformations that are possible for a cyclohexane. Okay, so let me just draw them for you. uh, we have chair conformer. This one is known as chair. Another same type of mirror image of chair is this one. This is also a chair. Okay, then we have half chair basically. Okay, so half chair is this one. Here is one carbon, here is one carbon. This is a half chair. Another, the mirror image half chair would be here is one carbon, here is one carbon. Okay, so this one is also a half chair. Okay, then we have another conformer, which is basically, yeah, so half chair, this was half chair. Then we have this twist boat basically. So twist boat can be drawn as like this. Okay, here in this case we'll be having this one as the front bond, twist boat. This is one of them. Another twist boat is same kind of structure, but in this case this one will be the front end. Okay, so this is also a twist boat. Then we have the envelope conformation. Okay, so this one is known as the envelope form. Envelope, yeah. Another envelope is also there, which is basically the mirror image of that one. This one is also an envelope. Then we have the last conformation, which is the board conformer. Okay, and among all these conformers, let me just mention the the planar structure of cyclohexane, which is this one. Okay, this is not a conformer. This is basically according to the Beer-Stein theory. Okay, so first of all, you must you must need to know that these are basically all the types of conformer that a cyclohexane is has basically. Okay, now let us we have to see whether which of them are stable and which of them are least stable in accordance with the the graph that is there. So let me just firstly explain it to you what graph I'm talking about. Okay, so let me use another pen. So basically there are two pathways for from which we can determine what will be the exact let us say the conformation. Okay, so first of all there is a C2 pathway. Okay, the C2 pathway goes like this. uh, okay, let us leave this. We have this chair conformation. This moves on to the half boat basically, which moves on to the twist boat. Okay, then we have then again the sorry. Okay, then we have this chair conformer. Okay, so this is basically the twist boat transition state. I'm sorry, the half chair transition state. Then this is a twist boat. Then this is another transition state, and then we have the let us say the chair conformer. Okay, another pathway which is basically the which we known as the CS pathway. it is given as chair conformer. Then we get the envelope conformer. Then we have the board conformer. Again, then we have the envelope, and then we have the chair. Okay, so basically this is chair, this is envelope, this is board, this is again envelope, and this is chair. Okay, so basically for both of them, both of the pathways have like these two conversion pathways are from the rotation of from one chair to another chair conformation. Okay, and those of these conformations are followed from we can study it from a potential energy diagram. Okay, so let us study the potential energy diagram. Firstly, we will be looking at the CS pathway. So let us draw the conformation for CS pathway. Um, a graph basically. Okay, then we will be giving a line here. Okay, so this is the like in the right hand side we are in the x axis, y axis we have the potential energy diagram which is there in kilojoule per mole. Okay, and x axis we have the inversion coordinate. We will be starting from the chair conformer. One chair conformer is there. From this we have to move on to another chair. Okay, in the between we have the transition state which has the board conformer. Okay, and here we have the like board is the intermediate. Here we have the transition state which has the envelope conformer. Okay, again we have this envelope over here which basically they are at the same energy level. um, okay, and then again we will be like falling down to the chair conformer again. Okay, so first of all the graph moves up like this. Okay, then we get a board conformer here, then again it moves up like this, and then again it falls down. Okay, so from the distance between the board conformer and the chair conformer, the energy difference is 24.7 kilojoule per mole. Okay, 24.7 kilojoule, and this distance from the transition state, that is from the envelope conformer, it is 47 kilojoule per. Obviously all the values that are taken in kilojoule per mole. Okay, so basically like this one is also 47 as they are in level. So this energy you can just calculate if you like my subtract 47 from 24.7, you will be getting the value then. Okay, now this was the pathway for the this was the CS pathway. Okay, so let us now let us draw the C2 pathway. Okay, so I'll be using another okay, let us use this one. So the C2 pathway. Okay, so let me just insert a graph. Okay, then we have from I will be inserting one line here. Fine. So we have this our potential energy over here which is also there in kilojoule per mole. Okay, we have the inversion coordinate over here. Okay, so first of all we will be starting from the first chair conformation. Okay, then we will be like having an intermediate or and a transition state over here which has the uh, half boat basically. Okay, I'm sorry. Yeah, so the conformation is half chair basically. Okay, not half boat, half chair. Then we have will be falling down to this part where we have a twist boat over here and twist boat over. So I'll be drawing the structures later. So let me just finish the overall techniques. We have another half chair over here, and then we'll be directly falling down to the another chair conformation. Okay, so basically what would happen is this part will be going up, then it will be meeting up here, then again this will be going up, and then again it will be falling down, forming the chair conformer. Okay, now here also one a few amount of energy is required to convert it to the, here we have the boat conformer. Okay, and in this case we have this twist boat, and here also we have this twist boat. Okay, so basically this is one twist boat, this is one, and this one is the other one. Okay, so this one is a chair, this one is the half chair, twist boat, boat, again half chair again, then and the flipped configuration of the chair. Okay, so basically this energy is around 43 kilojoule per mole. This energy, the gap between the chair and the twist boat is 23 kilojoule per mole. The gap between the twist boat and boat is 3.7 kilojoule per mole, and this is also 43, so you can just determine that 43 minus 23, so this one is around 20 kilojoule per mole. Okay, between the twist boat and the boat, this one, that is the half chair conformer. So you for this case this is the activation energy, that is 20 kilojoule per mole. Okay, so the bigger values that we have got is the 43 in the C2 pathway, that is from the conversion of chair to half chair. So half chair here is the most unstable in the C2 pathway, and in the CS pathway 47 is the energy gap, 47 kilojoule per mole is the energy gap between the chair and the envelope. So envelope here is the most unstable. Okay, so in the options you can see that chair, half chair, twist boat and boat. Twist boat chair is the most stable one. Twist boat basically is stable than the boat one, and then there is the boat, and the highest is the half chair. Okay, so like the most unstable is half chair. So the option that will be correct would be option B. Here would be the correct answer. Okay, because it has the highest potential energy, and therefore it is the most unstable, and that is the least stable. Okay, and so if we have to write the, if we want to write the order of the potential energy or the order of stability, chair, option A, chair would be the most stable, then we have twist boat, then we have boat, I'm sorry, boat is basically D, and then we have the last one, that is half chair. Okay, so this one would have been the correct order of stability if the question had asked. Other than that, the option B here would be the correct option. Okay, so like this was an extremely huge video, obviously, as you are learning since the confirmation of since my stereochemistry days, as I have already taught you. Okay, so let us end this video here. I hope you have learned a lot about the inversion of this cyclohexane structure, the flipping of that, the activation energy diagram, and not the activation energy, the basically potential energy diagram of different pathways, and in corresponding to that, the most unstable and the most stable species in the pathways. Okay, among all of the conformations. Okay. So thank you guys for this video. I'll see you guys in the next one, and in the next video we'll be starting again from question number 16. So thank you.